Good afternoon, everyone. It's a pleasure to welcome this afternoon Dr. Neera Jain. She's an assistant professor at Purdue in mechanical engineering. She runs a lab, and her lab has this, well, you can tell from the title of her talk, but she's interested in kind of systems theory, dynamics, control theory, but focusing, or one of her main focuses is in designing automation that works well with humans. And so she's really thinking about this idea of control-oriented modeling of human cognition. And she also works in energy systems. So Neera, she received her MS and her PhD from the UIUC, and she got her bachelor's degree from MIT. And she's been featured in NPR and Axios. She's a contributor for Forbes and writing in the topics of human interaction with automation. And we welcome you here today, Neera, and we're looking forward to your talk.
All right, thank you so much, Claire, and thanks for everyone for taking some time to listen. I know there's a lot of Zoom fatigue these days, so I certainly appreciate the attention. So today the title of my talk is Enabling Human-Aware Automation, a Dynamical Systems Perspective on Human Cognition. So let me jump right in. I'm going to actually, oops. I should have, there we go. I'm going to just turn on my laser pointer real quick here. Okay. So I think all of us have experienced the fact that our interactions with automation are increasing, not just in the workplace, but at home and in our daily lives. And I think the important thing that's motivating the work that I do and in this talk today is that the outcomes of these interactions still fall short of the intentions of us, the designers, and also the expectations that the users have of that automation. And I like to motivate this with this image that's was taken in the early part of the pandemic. I guess this is probably almost a year old now, in a hospital in Italy where they deployed several nurse robots. And this is a quote from the ICU director who said, "You have to explain to the patient the aim and function of the robot because the first reaction is not positive, especially for old patients." And you can imagine if you're this patient, you're sick with COVID, you're already scared, you're in an uncomfortable environment. There's so many different things that you're experiencing. Probably all you want to do is interact with a human nurse or human doctor. And then in rolls a robot that now you have to navigate. It's not what you potentially wanted. It seems foreign already in this kind of uncomfortable environment. And certainly the intent of designing this type of system is a positive one, is a good one, because it helps nurses and doctors focus their attention on more critical patients. It helps maybe the nurse and doctor to keep more distance from the patients and so forth. But again, in order for these technologies to have the impact that we want, we really have to be thinking from the perspective of the human user too. And so we know that there are several cognitive factors that affect human interaction with automation. And these have been studied for a very long time, particularly in the human factors and cognitive psychology communities. And they've, over the last several decades, developed these really nice qualitative frameworks that capture how complex these interactions are. And so here's one such diagram that captures a lot of these complexities. And I've highlighted a couple of terms in yellow that I'm going to be mentioning in the talk today. Kind of near the sort of center of this figure, we see reliance. I'll be talking about compliance today, but ultimately these words really get at the heart of whether or not the human is sort of chooses to interact with that automation. And so we can see the human's trust in the automation affects their reliance. The accuracy of the machine impacts that trust, which then again impacts reliance. We see that workload has an effect, and even other things like confidence, which I'll be mentioning at the very end of the talk. And this is extremely valuable, but what we really want are quantitative models as engineers that we can use to capture these behaviors. And indeed, different quantitative models have been used to predict things like dynamic changes in trust, and same with workload. But there are a couple of critical gaps that I focused on filling with some of the research we've been doing. The first is that in order to think about designing feedback controllers or feedback control policies that are responsive to these cognitive factors, we actually need a quantitative model that doesn't just predict trust, but specifically maps the automation outputs to those cognitive factors that are affecting decision making. So I really need an input-output model that makes sense in the context of control design. And then once I have that, I want to be able to then design control policies that ultimately enable adaptation of the automation to the human's cognitive state. And so this is what I'm going to be focusing on today. So the outline for my talk, I'll start out by talking about and defining what we call automation transparency. And this is really the control input at our disposal in these interactions. I'm then going to describe a POMDP model for two specific cognitive factors, trust and workload, that we've developed. I'll describe the human subjects experiment design that we created and implemented in order to collect appropriate training data for the model. And then I'll define the closed loop policy that we designed and then also validated, which was aimed at achieving trust calibration and reducing the human's workload during their interactions with this automation. I'm going to really briefly at the end talk about some clustering work that we've done since then for human trust models, and then wrap up with some conclusions and highlight some ongoing work. So let's start with automation transparency. So as I said, this is a critical, or in the context of these interactions, we've identified this as one of a few control inputs that we actually can affect during the human's interaction with the automation. And there are a couple different definitions of automation transparency, but the one that we use to guide our research is the following. It's the descriptive quality of an interface to afford an operator's comprehension about an intelligent agent's intent, performance, future plans, and reasoning process. And I've bolded these kind of 4 keywords. And I think it's useful to talk about transparency in the context of different levels of automation. And here, when I say levels of automation, I'm not referring to, for example, the SAE levels of automation that we're very familiar with now because of self-driving cars, but instead, I'm referring to an earlier definition of levels of automation that came out from the human factors community, specifically by Parasureman. So the lowest level of automation is called acquisition automation. And as it suggests, what it's helping the human to do is simply acquire information or raw information. The second level of automation would be automation that can analyze that information. So we call it analysis automation, and it would process that information and provide that processed information to the human. The next level of automation is decision automation, where the automation based on that processing makes a decision, which it then shares with the human as some recommendation. So the key here is that in decision automation, the automation still doesn't actually have the authority to act on that decision. It can only make a recommendation. And so a simple example of this would be Google Maps, which we all interact, or any type of mapping app that you might use, or navigation app that you might use. That's exactly, it can give us turn-by-turn directions, but it's up to us to decide whether or not we want to comply with those directions as we're driving. And then the final level of automation, which I've not pictured here because I'll be focusing on decision automation today, is action automation. So in that final level of automation, or highest level of automation, the automation not only can make a decision, but it has a control authority to act on that decision. And so self-driving cars, again, would be an example of that. And so we can think of transparency kind of in a reverse direction. So what do I mean by that? A low transparency automation would be one, or when the automation is using low transparency, I should say, what it's doing is it's communicating to the human the decision or the recommendation, but that's it. In a medium transparency automation, what's happening is that the automation is not only providing the recommendation or communicating the recommendation to the human, but it's also sharing some of the analysis or processed information that supported that decision. And then in the highest level of transparency, the automation goes one step further, and in addition to those other 2 things, it also provides some of the raw information that went into the processing that then supported the decision making. And so hopefully you can see how in this highest transparency case, you're really providing with the human with all of the information that they would need to sort of understand, again, the sort of reasoning process that the automation went through in order to reach a certain recommendation. So We know that automation transparency affects critical human cognitive states because of a lot of literature on this topic. And so more specifically, it's been shown pretty widely that increasing transparency typically leads to an increase in trust, which we can observe through an increase in compliance. So there's a strong relationship between trust and compliance as well. And similarly, typically an increase in transparency can also result in an increase in workload by virtue of the fact that you're providing the human with a lot more information in a higher transparency situation. And that increase in workload typically is reflected in terms of an increase in the response time of the human in terms of how long it takes them to make a decision as to whether or not they're going to follow that recommendation or comply with that recommendation. So understanding these relationships is important, but again, we're interested in thinking about how can we quantitatively capture these relationships. Well, it's useful to recognize two things. One, that the compliance and the response time are things or behaviors that we can actually observe. So I can observe whether or not the human did or didn't comply. I can also measure their response time. What I can't directly measure is the human's trust or their workload. So we call these are really hidden states in this context. And it's worth noting that there are other factors that also affect the state evolution, including the reliability of the system. Contextual factors can also affect the states and so forth. So given these relationships and these facts about the different variables, a logical choice for modeling these dynamics is a POMDP, or a partially observable Markov decision process. And very briefly, a POMDP is a 7-tuple that consists of states, actions, and observations, a transition probability function that guides the evolution of one state to another given an action A, an emission probability function that gives us a likelihood of observing O given that the process or system is in a state S. And then we can also design a reward function that can be maximized to actually design an associated optimal control policy with these dynamics. So this very nicely is sort of a probabilistic analogy to a state space model. So we want to use this POMDP to model human cognitive dynamics. And I should note that this is a very different way to use POMDPs. They're very commonly used in robotics, and typically the transition probabilities are often known. So we're kind of working in a different situation where we're now defining as the states of this POMDP the human's cognitive dynamics, the human's cognition. And what we're going to be using data for later is to actually identify what these transition and emission probabilities are. So we define two states, trust and workload, and for each one we simply define these as discrete random variables with either low and high trust, low and high workload. The actions that affect that state evolution are one, the transparency. Again, this is the one that we can control, and we define it as low, medium, or high transparency. We also include two other actions that we know would affect the state evolution of trust and workload. One of them being the actual recommendation itself, whether there's a stimulus absent or present, and the experience that the human has with the automation, or the experience that they had at the previous time step or trial, whether it was faulty or reliable. And then in terms of observations, we define the two that I mentioned on the earlier slide: compliance, either they disagree or agree with the recommendation, and then their response time. And I'll explain why we define this as a continuous random variable in a moment. And at this stage, I've defined these particular variables to be fairly generic, or at least independent of a very specific context. So for example, this recommendation, when I say stimulus absent or stimulus present, if this was a health recommender system, the stimulus might be the absence or presence of a disease. And I'm going to be talking about a reconnaissance mission context where the stimulus is the absence or presence of danger. In any situation where a human is interacting with some type of automated decision aid or some type of decision automation, we'll be able to measure or define and observe compliance and response time. So this is actually pretty generalizable to a lot of different contexts. So one important assumption that we do make is that trust and workload are conditionally independent. And what that enables us to do is actually identify separate models for the trust and workload. And it significantly simplifies the model. The other reason we did this was to improve interpretability of the model. So one of the things that I like to emphasize about this is that we don't just want to collect human data and use some algorithms to back out some mathematical relationship. We want to be able to interpret the model that we have. And so that's why we're trying to take more of what I would call a gray box approach here. It's worth mentioning that since doing this, we have actually evaluated and trained multiple coupled models of trust and workload, and that's under review, and I'm happy to talk about that work. And the main takeaway is that there is some coupling between trust and workload, but when we evaluated sort of model fit, there wasn't a significant improvement when you take in terms of the predictive capability of the model when you take into account that coupling. So we feel pretty good about this independence assumption. So I mentioned earlier that all of the states and actions and then compliance are discrete random variables, but the response time we actually model as a continuous random variable. And so I wanted to take a moment just to highlight why we do this. This is actually our own data plotted of response time, the probability density function of response time among the data that we collected. And you see that it's got this Gaussian like distribution with an exponential. And in fact, this is exactly an exponentially modified Gaussian distribution. And one of the things that we found when we were doing this work is that this type of distribution has actually been used for response time in the psychology community for several decades. So I actually cited a very old paper. This is probably the first one where this was used. And since then, the same distribution sort of shows up in data continually. So it's kind of fascinating. But we had actually previously considered binning the data and defining this in a discrete sense and found that using the continuous random variable worked a lot better. So that's why we made this choice. So having defined the structure of the POMDP model, like I said, what we need now is appropriate data that we could use to actually train that and identify the transition and emission probability functions. So we decided to use a reconnaissance mission study that we implemented online on Amazon Mechanical Turk in order to collect a large sample set of data to train the model. And this study was adapted from an earlier one that was published in 2015, but we did redesign all the transparencies that we used. So the objective for each participant in this study is to surveil several buildings in minimal time. And what we've built into the study is a trade-off between fast surveillance and their personal safety. And I'll highlight that here in a minute. And in doing the surveillance, the human participant would interact with a virtual robot, which acted as the intelligent decision aid in this context. And although we didn't communicate this to each participant, the robot was only 70% reliable. So again, there were going to be times in which the recommendation that the robot makes is not actually correct. And so let's walk through kind of one trial or one building to see kind of how this works. This will help everyone to understand the control policy later that we end up designing. So, oh, sorry, go ahead.
I had a really quick question. I was curious why the choice to make the robot not 100% reliable, but just 70% reliable?
Yeah, great question. So the reason that we made the robot 70% reliable is because we actually want to stimulate changes in the human's trust, because what we're trying to do is to elicit the trust dynamics of the human. And so reliability is one of the strongest influences on human trust when they're interacting with automation. So if the robot was 100% reliable, we would expect that the human participants would probably comply with the recommendation a lot. And we wouldn't be able to actually, if you think about this from sort of a system ID perspective, what we're trying to do here in a human subject experiment is essentially persistently excite the dynamics that we want to identify, which are in this case, trust and workload. So we made sure that we designed the study in a way that we're perturbing those dynamics. Does that make sense?
Yeah, and so then I guess there's another concept here, which is that I'm assuming that whatever control policy you are able to synthesize, or based on the data you collect from the 70% reliable robot, would also have to be different if you change that data to be from a robot that's like 50% reliable or 20% reliable.
That's a really good question. I mean, we never actually tried that. So the short answer is I think you're right. I mean, that would change the dynamics. Although, if the robot was just more, that's a really interesting. Let's come back to that because I'd be very curious. We never even tried that to see if how well the model that we trained would work in that other scenario. I think it would actually still work reasonably well. But you're right that certainly this reliability does, again, obviously affects how much those dynamics are perturbed. So yeah, great thought.
Thanks.
So in one, so let's walk through one interaction that the human has with a building. And what I was about to mention was that each participant participated in 3 missions, and each mission had 15 buildings. And what changed between those missions was the transparency that the robot was using. So we were also collecting data to not only perturb these trust and workload dynamics, but to see how the human responded, or how that dynamic changed when the transparency of the robot itself was different. So the human would be told that they were in front of a building, they'd see a picture of a building, and they'd be told that the robot is going to go in and search the building, and this would take somewhere around 4 seconds. The robot would come back out and report that either it had sensed no danger or that there were gunmen present, and accordingly make a recommendation as to whether the human should wear light armor or heavy armor before they go in and surveil the building themselves. And let's say the recommendation was to wear light armor, and the human went ahead and decided to comply with that recommendation. So they'd click light armor, they'd go in to surveil the building. And if there was actually no danger, then awesome, that was the correct choice for them to make, and they go on their way. If they went into the building and there actually were gunmen present, so the robot maybe had been wrong in that case, then they would be hit with a 20-second penalty because they had gotten injured. And so this 20-second penalty was pretty significant. And even in the study, we actually made them wait for a full 20 seconds before they could advance to the next building. And so this, remember that I'll keep coming back to this particular case, because this is, again, the biggest penalty that the participant can incur when they're participating in the study. The alternative would have been for the human to say, you know what, I don't want to wear light armor, I want to wear heavy armor. If they were to do that, then regardless of whether there is danger or isn't, they don't get hurt because they've got the heavy armor on. So it takes them 7 seconds instead of 3 seconds to put on heavy armor. So there's the penalty for putting on the heavy armor, but then they don't get hit with any additional penalty. So that's where how we've built in the trade-off in terms of fast surveillance, but then their personal safety. We randomized the order of the missions across all the participants to avoid any ordering effects, and we got data ultimately from about 200 people. And I mentioned again the different transparency levels, which are important here because that's our control input. So if we don't have any control authority with that, then that's a problem. So we really want to make what we're looking for in our model when we ultimately train it is to see that using different levels of transparency can actually affect the state transitions or the state dynamics differently. So in the low transparency case, this is what each participant would see. Again, they would make a choice of light or heavy armor, and they were just told the report and a recommendation, nothing more. In the medium transparency case, in addition to this report, they were given this kind of danger potential threshold sensor. And so this blue bar would either be above or below the threshold. And it was an indication of how confident essentially the robot was in terms of having detected a threat or not. And in the highest transparency case, we provided all of that information, but the additional raw information or data that was shown were 7 thermal images that we would show the participant at the bottom of their screen. So they could actually take the time to look through these themselves to see if they actually maybe could make out a human form, for example. So again, you can see how this provides them with even more information to kind of double check the recommendation of the robot, but they also can incur a lot more workload or time in evaluating those images. Okay. So we collected all that data, we trained our trust and workload models. I'm not going to go through all of these figures, but I'll highlight a couple of things to kind of give us some intuition about the model. So if we look at the emission probability function for the trust model, this characterizes the trust compliance relationship, which we know is a pretty strong one based on the literature and study of this. And in fact, we do see that if the human is in a state of high trust, they are very likely to comply or agree with the recommendation, much less so disagreeing. And if they are in a state of low trust, they're very likely to disagree with the recommendation, and maybe very seldomly they might agree with that recommendation. So this made sense and was consistent with what we expected to see. If we look at one of the transition or a set of the transition probability functions for a particular set of actions, in particular, this is when the recommendation made by the decision aid or the robot is to wear light armor. And at the last trial, they made a reliable recommendation. And these different colors recommend how the transition probabilities change with different transparency. And so if we look here, what this is saying is that using highest transparency, which is in the sort of dark red color, has the highest likelihood of transitioning the human from a state of low trust to a state of high trust in this particular, given a light armor recommendation and a last reliable trial. We see slightly lower probabilities with the other transparencies. Interestingly, if we look at transitioning from a state of high trust back down to a state of low trust, it's again the highest transparency that actually has the highest likelihood of causing that transition. And so what this actually tells us is that we have the most control authority with high transparency. And in fact, it's going to be better for trust calibration, which I'll talk about in a little bit. If we look at the workload model, here, again, because it was a continuous random variable, we have these probability density functions. And what we can see is that when the human is in a state of low workload, we see that there are very low response times and a much kind of shorter or steeper emission probability function here. And if the human is in a state of high workload, we see a much larger distribution of response times that also stretches out to much longer response times, which again makes sense because we know that higher workload tends to lead to a higher response time. And then we can look at a similar set of transition probability functions for the workload model. Again, light armor recommendation and a last reliable trial. And what we see this time is that there's the highest transparency in maroon that has the highest likelihood now of transitioning the human from a state of low workload to high workload, which again makes sense. And we also see that if the human is already in a state of high workload, showing them high transparency is going to basically keep them there because of, again, and it's really those thermal images that increases the workload of the human. So with our trained POMDP model, we now have, we're now ready to be able to design some type of model-based feedback control policy, again, because our ultimate goal is to actually adapt the transparency to the human in real time based on some reward function. And so the nice thing, again, about a POMDP is that we can go ahead and it's sort of pretty straightforward to define a reward function and solve the POMDP to obtain that optimal policy. And so then we had to ask ourselves, well, what should the control objective be? And so the way that the experiment was set up, really the objective of the human in that context was to minimize their emission time. And if we thought about the model observations in the states, there's two ways that the human can minimize their emission time. One of them is by reducing the number of incorrect decisions they make, which really is related to their trust being appropriately calibrated to the human and the word to the automation. And the word calibrate here is important because, again, we don't want to actually maximize the human's trust. We want the human in all these different kinds of human machine interaction contexts to know when they should trust the automation. And we also want them to know when they should not. So distrust is just as bad as overtrust. So we really want to help them calibrate that. Similarly, the other way that they can minimize mission time is simply by reducing their response time, which is related in terms of states to reducing their workload. So what we decided to do was to actually define two reward functions, one aimed at each of these objectives. So we call those decision rewards and response time rewards. So as I mentioned, the decision reward is maximized when you're calibrating the human's trust. And what's important, and this kind of gets back to the earlier question, trust calibration only really comes into play if the robot isn't always correct. And in a lot of these situations, the robot wouldn't always be correct. So this is a pretty reasonable assumption. And so I've got this matrix down here where, again, I told you that it was 70, we had designed it to be 70% reliable. So basically that means that there's a 70% chance of a true negative or a true positive, 30% chance of a false positive or a false negative in terms of the robot's recommendation compared to the true situation. What we do in defining the decision reward is to define it in terms of the human's choice in the true situation. So what do I mean by that? So if the human chooses to wear light armor and there are no gunmen present, so the gunmen are absent, then it takes them 3 seconds to wear the armor or to surveil that building, as I mentioned earlier. And however, if they put on light armor and there were gunmen present, they spend the 3 seconds to put on that armor, plus they get hit with that 20-second penalty, and they end up incurring it takes them 23 seconds to surveil that building. And then similarly with heavy armor, it's 7 seconds no matter what. So what we decided to do was to actually define the penalties associated with this reward function to be equivalent to the time in seconds that it would take them to surveil the building in these different situations. For the response time reward, that's simply maximized when workload is reduced. And so we took a really simple approach there and just defined the response time reward to be the opposite of the response time. It's worth noting that as I've defined these here, I've defined them in terms of observations, but we did transform these reward functions so that we could derive the expected standard reward functions in terms of states and actions. And in a real situation, you could imagine that either one of these rewards might be more important. It might be more critical to make the correct decisions that, if getting injured is, really needs to be avoided, for example. Or perhaps the situation is such that minimizing time at whatever cost is the most important. And so what we ended up doing was defining a total reward as a weighted sum of those two other reward functions, where we can use this factor zeta to basically trade off between them. And then we also defined this discount factor to basically give more weight to essentially 15 trials, which was the length of a single mission. Okay. So we ended up solving the POMDP and solving for the optimal control policy for 3 different values of zeta. So I'm going to walk through those 3, and what we've done here is sort of visualize the static control policy to get intuition about what's happening. So in this first case, we consider a zeta equal to 0.95, and just to kind of go back here for a moment, what that means is that we're giving most of the weight to the decision reward, very little to response time reward. So in other words, I'm saying I want to make sure that the human does not make incorrect decisions, even if it increases their workload a bit. And I've got 4 different graphs here. Each one corresponds to a particular recommendation and the other action, which was the whether or not what we called experience of the human with the automation at the last trial. And then on the y-axis, I'm plotting the probability that the human is in a state of high workload. On the x-axis in each figure, I'm plotting the probability that the human is in a state of high trust. And I want to draw your attention to these top 2, which are what we call the high risk cases. This was, again, when the recommendation is to wear light armor. So this is now when the human is at risk of incurring that penalty if the automation is, or if that decision aid is actually incorrect. And the really, really risky case is this one here on the right, when the automation was actually reliable at the last trial. So you can imagine that if the last building you went to, or when you went to the last building, the robot made a correct recommendation, and now it's telling you to wear light armor, you might be that much more likely to go ahead and say, yeah, why not? I'll go ahead and wear light armor. In this particular case, what we see is that when the human is very likely to be in a state of high trust based on our belief state estimate, the optimal thing to do is to show them the highest level of transparency. And when we first saw that, I'll admit, we actually, I told my student, let's double check this because typically you use high transparency to actually increase the trust of the human. And so it did not make sense at first to see that the optimal thing to do when a human was already in a state of high trust to use the highest transparency. And what we realized, though, was that what it was doing was trying to mitigate the potential of overtrust, the potential negative impact of overtrust. So if the human is very likely to be in a state of high trust, and they're being told to wear light armor, and the automation was reliable the last time it made a recommendation, then this person is really getting set up to potentially incur that 20-second penalty if the robot happens to be wrong. And so essentially what it's saying is, hold on, in this particular case, it's worth it for you to take the extra time, look at these thermal images just to make sure that I'm telling you the right, that I'm giving you the right recommendation. And so we thought that this was really exciting because one of the things that I think is really difficult to mitigate in these human automation interaction situations is overtrust. And so this showed that just from the data that we collected and having trained this model, it was able to tease this effect out. If we back off zeta a little bit and decrease it to 0.91, so still pretty high, still we're really weighting the incorrect decisions over the response time of the human. What we see is, particularly if we look at this upper right figure again, is a pretty similar policy. Basically, the probabilities over which it's optimal to use the highest transparency shrunk down because, again, of the increase that it incurs in terms of workload. So if we back off on zeta and say, well, I really don't want the participant to increase their response time rewards, then the optimal thing to do is to try to mitigate their overtrust with medium transparency and only use highest transparency in those kind of extreme cases. And then if we back off zeta all the way down to 0.5, what we see is that it's never optimal to use the highest transparency, again, because it led to such a high workload that, again, in that case, the optimal thing to do was to just try to use medium transparency a lot of the time to hopefully mitigate overtrust. Was there a question? Okay. So this was really exciting just to even see these control policies and see that they, made sense. But then we went ahead and wanted to actually validate them and see if they worked. And so what we did was we conducted another round of human subject studies, the same reconnaissance mission, 3 missions, 15 buildings each, and we defined or implemented 2 different studies to do a between subjects experiment, where in study 1, which had about 100 participants, the participants either saw just high transparency all the time or a variable transparency based on either the zeta 0.5 policy or the zeta is equal to 0.95 policy. And these were, again, randomized across participants, so to avoid ordering effects. In study 2, the participants either saw a fixed high transparency all the time, fixed medium transparency, or the variable transparency. So again, they didn't know a priori when they started a mission whether the transparency was going to stay the same the entire time or that it was going to change, and they didn't know on what basis it was changing. So they weren't informed at all that there was an algorithm potentially, or that there was an algorithm determining what transparency they should see, again, based on an estimate of their trust and workload. So we can summarize all of the data in this plot, and I'll walk through this in a couple steps. So again, by including some experiments where we showed only a single transparency, that's kind of our open loop results as sort of a benchmark. So if we just look at cases where the participants saw either all low transparency, all medium, or all high, we see that, again, as expected, when high transparency is used all the time, the decision rewards are maximized. If the human is provided with all of that information, that transparency at every building, they're almost always able to make the correct decision in order to basically calibrate their trust. However, that comes at a big cost in terms of the response time rewards. Interestingly, we see that medium transparency really improved the decision rewards with actually very little penalty to the response time rewards. So what that does suggest to an extent is that maybe this we did a really good job of designing this medium transparency, and that we provided just enough additional information to the human that helped them to make better decisions, but didn't take so long to evaluate. If we now look to see how the rewards compared between the different closed loop policies, we see, again, what we expect, that as we increase zeta, we in fact can balance this trade-off that we wanted to between response time rewards and decision rewards. So exactly we see, again, for increasing zeta, response time rewards go down, decision rewards goes up. And so the takeaway here is that with this control policy, we actually were able to mitigate those two explicit rewards while the human was in real time as they were interacting with this automation. One of the interesting things that you might notice is that showing medium transparency all the time did do pretty well compared to this 0.91 policy. And one of that we outperformed with a closed loop policy slightly on decision rewards, but we did incur more of a response time penalty. And one of the things that we didn't take into account that we'd like to do in the future is that we didn't actually, our dynamic model didn't account for any penalty or in time that's incurred from switching the transparency. So again, our open loop data was collected based on the human seeing a single transparency over emission. And so you can imagine that in some of these closed loop studies that we did, if they had seen maybe 2 trials of high transparency, and then the next building that they surveil, all of a sudden they're seeing less information, that could have actually created some confusion among the participants. So that's one thing that we do think could actually further improve some of these closed loop results. So to summarize this part of the work, we've seen that we know that human cognitive behavior plays this really important role in human decision making as they're interacting with all different kinds of automation. And so what we set out to do is to, again, take this dynamical systems perspective on modeling human cognition and use a POMDP modeling framework in order to capture the dynamics of trust and workload so that we could then, again, design a closed loop policy that actually can be aimed at calibrating the human's trust and reducing their workload. And what we were able to show is that indeed, with this policy, we saw that we were able to balance explicit trade-offs that we had designed into our reward function. So we've done some different things since then. All the work that I just presented is largely a part of an article that we just published in December in a special issue of Control Systems Magazine on cyber, physical, and human systems. So if you want to see that, that's where that work is. And using that, in that work that I shared, we trained a single POMDP model by aggregating the data of, approximately 200 participants. But I think a really important question that follows from that is, is a single model representative or appropriate for all humans? And that brings us to sort of this question of, you could have either one generalized model, which is what we did. The other extreme is to have individualized models for every person, but this might be very impractical. Certainly we can't train a POMDP for a single person without collecting a lot of data from that one individual. And so one of the questions that arose was sort of, well, are there dominant trust behaviors? And here we specifically focus on trust. And can we cluster the human population maybe by these behaviors and maybe just have a couple of trust models that reflect most populations? And so this was work that we did and published also in December at the IFAC CPHS conference. And again, it was the same data from that reconnaissance mission study. And we applied clustering algorithms to the data where we actually kept retraining the data and sort of clustering individuals until we found that each participant was in a model that, or was part of a model that maximized their log likelihood in terms of prediction of their behavior. And we tried a couple different numbers of clusters and ultimately found that we got the best results when using 2 clusters. And we named these the followers and the preservers for the following reasons. So if we look at just some quick behavior, the followers, if we look at the percent of trials that they were injured, they got injured about 10% of the time. With the preservers, it was much lower. And so basically we called the followers because they were highly compliant, as we can see from this curve down here. So this is the percentage of compliant trials. The followers were compliant some 86% of the time. The preservers, on the other hand, were only compliant 70% of the time. And in particular, we saw that whenever they were given a light armor recommendation, they almost always chose heavy armor instead. So they were very averse to getting injured in that particular situation where they put light armor on, but the robot is incorrect. And interestingly, Again, we did not tell any of the participants that the robot might be unreliable, and obviously didn't provide the exact reliability of it. And it's very interesting to see that the preservers, their compliance was 70%, which aligns actually very closely with the reliability of the robot. And so we had trained a separate POMDP for each of these groups. And so what we thought would be interesting to do is to actually solve each of those POMDPs using the same reward function I described earlier. And I think we did this for a zeta value of 0.91. And what you see are drastically different policies for each of the two groups. So for the preservers, the optimal thing to do a lot of the time, and this is again, this upper right-hand quadrant is the case, was that high risk case. The optimal thing to do is to show them low transparency because even if the recommendation, or when the recommendation was light armor, they were so likely to not comply because they just said, forget it, I'm not gonna, I don't wanna, they're very risk averse, I don't wanna take any chances, I'm just gonna put on the heavy armor, that there was no point in having them incur any type of workload penalty because they weren't gonna get hurt because of the way that, because of their propensity for risk aversion. Whereas the followers were so compliant that when a light armor recommendation was made, the optimal thing to do was pretty much to show them high transparency across the board, regardless of what their likelihood of trusting was, or being in a state of high trust was, because they were so compliant that they probably would wear the light armor and then get injured. And so this, again, really highlights, one, the need for, tailoring some of these models to certain types of behaviors. But I think it also says that we don't necessarily need entirely customized models to different individuals, that there are some dominant behaviors that we as humans kind of fall into. And then my last slide is this one on just a quick smattering of related work that we've been doing in the space of modeling and control for human automation interaction, again, with an emphasis on trust. So we have some earlier work where we were looking at psychophysiological data in order to estimate human trust. And specifically, we had, I think, the first paper where we used electroencephalogram data as well as galvanic skin response in order to actually build a classification model that would classify the human as being in a state of high trust or low trust. All the work I showed today was just using behavioral data, and we think there's a lot of opportunity and promise to considering psychophysiological data in addition to behavioral data. We've extended our framework to action automation. So we have a paper where we use the same POMDP framework that I shared earlier for trust and workload, but now in the context of a self-driving car. And then our ongoing work, which I wanted to very briefly mention, we've now been thinking about, let me move this for a second. Our ongoing work is thinking more deeply about sort of the cognitive states, specifically in contexts where the human is now sharing control with the automation, and also where the human is learning and building skill during their interaction with that automation. So we're trying to now think about estimating cognitive states in these more complex and nuanced interactions with automation. And so we're getting ready to submit a paper where we're now thinking about self-confidence in addition to trust as it relates to human reliance in some of these shared control contexts where maybe there's not a binary choice between not relying and relying, but it's more nuanced where the human has a choice between discrete levels, for example, of reliance. So with that, I can see I'm nearly at the end of the hour. So thank you for your attention. I just want to acknowledge a couple of important people. One of my collaborators, my main collaborator in a lot of this work is Professor Tahira Reed-Smith. She's an associate professor at Purdue. She is an expert in engineering design and uses a lot of the psychophysiological sensors in her research on human-centered design and has been a great partner. And most of the work that you saw today was done by my former PhD student, Kumar Akash, who's now a scientist at Hunter Research Institute, not too far from Berkeley, actually. And then I also wanted to highlight a lot of that work was also supported by an excellent undergrad who's now at UPenn in robotics, Griffin McMahon. And then Dr. Wanlin Hu and Caitlin Polson also helped with some of our earlier work. So thanks again for your attention, and I'm happy to take any questions.
Yeah, thank you so much. I'm going to stop the recording and we can go ahead and open up for discussion.